Good morning, grade 11s. Welcome to Monday morning, and I hope you had a good weekend. I hope on Friday you were able to watch the couple of videos, the one that I made, and then the video on the Tacoma Narrows Bridge. I always like watching that video. It is fascinating to me to see a concrete bridge sway like that, so dramatically, and then to collapse into the water. And so I hope you found that interesting as well. And again, that's what engineers have to take into account when they're building things like that. And so today, we're going to move on to other ways that sound and physics and music go together. But before we do that, let's talk about our verse of the day today. Our verse of the day today comes from Psalm 46, and it says the following: God is our refuge and strength, an ever-present help in trouble. Therefore we will not fear, though the earth give way and the mountains fall into the heart of the sea, though its waves roar and foam, and the mountains quake with their surging. And then later on in Psalm 46, two more times, it repeats itself saying, the Lord Almighty is with us. So take that with you today. Know that A, the Lord is Almighty, and B, that He is with you at all times. And so now let's move on to what we're going to talk about is resonance in air columns. So if you've ever played a trumpet or a clarinet or a trombone or any kind of instrument that uses air in a tube to produce sound, that is the theory we're going to look at today. Again, I'm not a musician, although I did play the trombone in grade 9, my one and only year of playing the trombone. Oh, and before that, when I was much younger, I had a few lessons on the accordion, believe it or not, and I could play a few songs on the accordion way back in the day. But not a musician, so we can talk about the theory and how it works, but I won't be able to play anything for you. All right, so before we do resonance in air columns, again, remember that resonance is a matching of frequencies so that we can match two frequencies and then get a maximum amplitude, which will be a maximum amount of sound. Way back when we first started talking about waves and wave properties, we talked about waves reflecting off of a fixed end or a free end, and how when we produced a wave that had in a medium that then reflected off a fixed end, the reflected wave was inverted. And if we found the right frequency, we could produce a standing wave. So remember, I did a little demonstration with the spring where I created a standing wave, a wave that appears to not be moving. Okay, so that's what we want to, that's the theory is when we create sound in an air column. And a column of air, okay? And so I'm going to do a little demonstration here momentarily with a tube that is going to be submerged in water, which will create a closed end, and we'll be able to find where we get the resonant frequencies, where we get the loudest possible amplitude. And so what happens is we're going to produce a sound at the top, and so, or in our case, it's the top at one end of the column. So if you're playing a trumpet, wherever your mouthpiece is, same with the clarinet, anything like that, you're producing a wave coming at one end and it's moving down. And then if it's a fixed end, it's reflecting back. If it's an open end, it's also coming back, but in a different manner. We'll talk about that momentarily. That one I can't demonstrate quite as nicely, but you can just imagine it. Okay, so what happens here is this. If I have a nice short column, here's a nice short column, to produce a standing wave, I'm going to find a frequency that's going to produce a standing wave. What's going to happen is that wave will travel down, and when we have a fixed end, there's always a node at one end, right? Actually at both ends, but here since it's open on the other end, we're not going to get a node there, but at a fixed end, we'll always have a node at the fixed end, okay? And what we want to do is we want to find where we get the maximum crest, right, in our standing wave. So where are the two, the one that's going one way and the one that's going the other way, is that amplitude the largest, right? And what we see is that that's going to be at a quarter of a wavelength, right? Because again, it's half of a crest. A crest is half of a wave, and we have half of that. So that gives us a quarter of the wavelength. And so what we're going to find is we're going to produce a frequency at the top, and when we find the right frequency, it's going to give us this standing wave. where at this distance, which will be equal to 1/4 of the wavelength, we will get the loudest, the greatest amplitude of sound, okay? And that's called the first fundamental, okay, or the first resonant length of an air column, all right? And then we can move to the second resonant length, which now, again, we're just going to increase it, and we're going to find the next point, because again, it's a periodic wave, it's going to continue. We're going to find the next point where this opening, this largest amplitude happens. All right, and so again, you'll have the node at the closed end. You'll have a node up here where, again, the waves cancel out, and then you have your largest amplitude. All right, and again, now, previously we had from node to loop, L stands for loop, as 1/4 wavelength. Now we're adding another half wavelength to it, and so that second resonant frequency, the second resonant length will happen at 3/4 of a wavelength, and so on. So every resonant length is going to be a half wavelength further along. Okay, so the next one would be at 5/4 wavelengths, and so on. All right, so we got air, sound waves traveling down, reflecting off the bottom, coming back up, producing a standing wave, and then we're looking for the resonant lengths, which give us the greatest amplitude, and that's what produces a nice sound for us to hear. All right, if we had an open end, so again, open ends are more like a lot of the instruments we play. An open end reflection, or a free end reflection, the wave that comes back is not inverted. Okay, so what that does is it produces a loop at both ends of it. Okay, at the end, that's where the frequency is being produced, and it also produces it at the other end. And so again, when we're making instruments, we have to make them at a particular length so that we have that opening at both ends of our instrument. Okay? And again, for each note, it's going to be a little different because each note has its own frequency, which means it has its own wavelength. And again, now when we do this, the resonant lengths happen at a half wavelength to start. The first one's at half the wavelength. Again, we got both loop to loop, which is a half wavelength. And then again, it's going to add a half wavelength for every other resonant length. Okay? We're going to move into, now I'm going to do a quick demonstration here. I'm going to move my camera, see if we can do this without making you too dizzy. Okay. Ooh, look at that. Okay, we're going to place it here. All right, so here's what we have now. All right, so here's a column. It is full of water. You may or may not be able to see that, but it is full of water. You can see the water level changing as I move this up and down. All right, so what we're going to do is, since this is movable, this is going to create our column of air, right? The water level is the bottom, and that creates a closed end. So when I create a wave, sound wave at the top, it's going to travel down, reflect off the water, and come back up. All right, so I'm going to create a sound using this tuning fork, which is a C, it's 512 hertz. All right, a quick calculation would tell us that our wave formula, which is velocity equals frequency times wavelength. If I want to find the wavelength, I'm going to do velocity divided by frequency. I did a quick calculation. The air temperature in this room is about 20 degrees, but this water in here is a little colder, so the air in the column of air is going to be a little cooler. We get around 340 meters per second. 340 divided by 512 is approximately 66-ish, 67-ish centimeters. Okay? If I divide that by 4, if I take 1/4 of it for our first resonant length, that's around between 16 and 17 centimeters. So what I should find is that when I produce a sound at the top here, and I make this length of air 16 to 17 centimeters, we should hear a louder sound. Okay, because when I hit this, you're not going to hear much, because tuning forks don't make a lot of noise. But what you'll find now is if I raise this up, right about there, it gets nice and loud. And if I take and I measure this now, oops, I just made it go down, so it's not going to be exact. But if I go from the water level to the top, oh, look at that. It is 16.2-ish centimeters. So it's pretty much bang on. Again, we estimated the temperature of air in the column, and I didn't do the calculations exactly, so there's some rounding off in there, but we're getting around 16, which is where we would expect it to be. And so you could hear it. We'll just do it one more time here so you can hear the louder noise. Okay, so this is just a nice quiet. As I raise this, listen carefully. There, right there, it's loudest. Okay, if I go lower, not very loud, higher, there it is. Okay, so that's how it works. And so when we're producing musical instruments that use a column of air, we are producing them at a proper length so that we get the greatest clarity, the greatest quality of sound from it. And this doesn't have to be a column. It can be as simple as a block of wood. Okay, you've all in the past probably at some point made a homemade xylophone or a glockenspiel out of various pieces of lengths of wood, okay, or metal or whatever you want to use. To produce the right notes on those, your pieces of wood or metal have to be the appropriate length so that you're going to get the nice resonant sound. And so that's how instruments are made that use columns of air or use waves, sound waves, traveling through a medium, either off a closed end or an open end. And again, I can't show you the open end, but you can see the closed end. All right, you're going to do a little bit of reading out of your textbook today, and there's a couple of questions as for your assignment, and then we will come back tomorrow. We'll see you then. So have a great day, and if you have any questions on your assignment, make sure you're emailing me and asking them. See ya.